EMF and terminal voltage. A battery is both a source of voltage and a resistor. Each battery has a source of electromotive force, and again, let's just quickly review that terminology. That's a horrible, outdated term from the 1800s, and really all it is voltage, okay? But it historically was called electromotive force, and it's not a force, it's voltage, but we've kept the name. It's abbreviated EMF, probably because people were embarrassed to say electromotive force, but what that does is that's the actual chemical process that carries charge from low to high voltage, chemical and electrical process. Another way to think about EMF is that's the voltage you measure when there's no resistance connected to the circuit. Let's see what that means. This dashed line here is, we're going to represent that as a real battery. That's our real battery delivering a voltage. Inside of it is the EMF. This is the chemical process that gives energy to the electrons, converting chemical energy into electrical energy. And then inside the battery, you don't put a resistor there. Nobody designs a battery with a resistor, but we can represent the various chemical processes inside the battery and how they actually oppose current by this little r. So this is not a real resistor. It is a symbol for the energy that is taken out of the battery before that energy comes into the circuit. Terminal voltage, V sub T, is the voltage measured when a voltmeter, so let's take a voltmeter here, symbol is V for voltmeter, is hooked across each of the terminals of the battery. Remember, this dash box here is representing the physical battery. If there is no circuit attached, for example, if I have an open switch here, no current is flowing, so when I measure this voltage, I don't even see this resistor. I just see the energy of this battery. So the terminal voltage will equal the EMF. But once I close this switch and there's current flowing, I'm going to have a voltage drop here. So what I'll be measuring, this terminal voltage, V sub T, will be the EMF minus the current times this resistance. So that would be E minus IR. The terminal voltage now is less than when there was an open circuit. A common example is if you have a car battery and it's not turned on and a mechanic measures the voltage and it says 14 volts, which is good for a battery, and then you try and turn it on. But if the battery is old, the chemicals are getting somewhat used up. Again, I'm not a chemistry teacher, but the battery has a large internal resistance. Again, that's not a real resistor, but it's not working as well as it should. So when the current comes through, when you close the switch, you're going to have a huge voltage drop here. And that may drop you below the amount of voltage you need to start your car. So it looked like 14 volts when you measured it without current going through. But once you close the switch and current went through, your terminal voltage is less than the EMF. Terminal voltage, which is measured between this physical point on the battery and this physical point, is the EMF minus the current flowing through the battery and then through the circuit times the internal resistance, which again is not a real resistor. It's a representation of the processes in the battery that reduce the current. And over time, that internal resistance gets greater. Terminal voltage is a maximum when there's no current flowing. If there's no current flowing, the terminal voltage is EMF. Now, we can treat this resistor as a normal resistor when we solve for equivalent resistance. So if we want to find the current coming out of this battery, we have to add this resistor, the internal resistor, plus the external resistor to get equivalent resistance, and then the current would be the EMF divided by R equivalent.